Good day, class. So we are now on the second to the last topic of the review for heat and mass transfer and separation processes under the unit operations courses for chemical engineering review 4. And for now, we'll be talking about leaching. Now let's first go to the basics and the fundamentals of leaching. So in terms of its definition, it is the extraction of a soluble constituent from a solid by means of a solvent. So this time, our solute is coming from a solid and our solvent is liquid. Now, the soluble material is dissolved from its mixture with an inert solid by means of a liquid solvent. So, our material, specifically our constituent referred here, or the solute, is together with an inert solid, meaning this inert solid portion of your solid will not whatsoever be dissolved by your liquid solvent. So, your liquid solvent will selectively only dissolve the constituent or the solute from the given solid matrix. Now, a special leaching process or majority of the leaching processes that are used not in the industry but on a natural setting is just simply using water. So in our case here, we are recovering a desired substance through the use of water. That particular solid that we dissolve using our solvent water is of course processed by the special term used in leaching. Actually, this is still leaching but only referring to leaching which uses water as the solvent, and that particular term is washing. So we simply wash off the undesirables or the other inert solids that are present in our solid matrix, and we want only to recover that constituent or that solute from that given solid matrix. If water is used as the solvent, then the process is simply referred to as washing. Now, what are the principles of operation behind leaching? So, we have to consider the contact, the separation, and the extraction process. Now, when we speak of the contact, it refers to the solvent interaction with the solid matrix. So, it will selectively take out the solute from the solid matrix. When we speak of separate or separation, it will now separate desired substances from the solid matrix using the solvent. And last will be extracting desired substance from a collection of substances, just in cases wherein our solvent takes out not just one component from our solid matrix but several components. So there's a need for us to further use extraction. That way we can selectively take out that particular solute that we are interested in. Now, the operation for leaching can be batch, semi-batch, or continuous. It can be operated at an elevated temperature to assist in the dissolution of the solute in the solvent. Now, flow is most of the time, so not all the time, but most of the time essentially cross-current or counter-current. So, it's not parallel, but rather cross-current or counter-current. Now, the amount of soluble material removed here is often greater than in ordinary filtration. That is why we're using leaching. And the properties of the solids may change considerably during the leaching operation. So, as we can say, our leaching process is a modification of the filtration washing, which is just simply taking out a particular solute, but in terms of purity, it might not be as pure as if we are to employ leaching. Now, what are the important factors that we need to consider when we want to leach out a particular solid from the solid matrix using a liquid solvent? So, we have to consider the particle size, the solvent characteristics, the temperature of operation, and if there's a needed agitation, or if there is an agitation, what is the degree of agitation that is needed for the desired recovery. Now, with the three factors considered in leaching, we are to look into first temperature, because this one is very important, just like as the area and the contact time needed. So temperature here is adjusted to optimize. So it has something to do with recovery, enhancing the percentage of recovery. So that is why the purpose is to optimize solubility and mass transfer. That's the purpose of operating leaching at an elevated temperature. Now in terms of contact time and area, so in terms of liquid to solid contact, it is essential for the extraction to take place and maximize contact area per unit volume, which will, of course, in terms of requirement for equipment size, it will lessen the size of the equipment. So as much as possible, we want to increase the surface area and we want to increase as well the contact time. That way, in that manner, we will be able to, shall we say, save in the capital expenditure of acquiring a much bigger equipment that will facilitate the leaching operation. Now, in terms of solvent selection plays a very important role in solubilities as well as the separation steps that may follow. So, if your particular solvent does not selectively only dissolve your solute but may carry with it other constituents of your solid matrix, there is a need for you to employ other extraction processes. That way you can only at the last part of the process only get hold of that particular constituent or solute that you are interested in. Now, nearly all equipment employs some type of agitation so as to increase the mass transfer, to aid in mass transfer, and to ensure proper mixing. So these are the three important factors that aid in leaching from our CHE resources. Now, as to the process overview, the things that you need to understand prior to the simple overall material balance that you are to employ in leaching processes, there are terms that you need to understand, and there are concentrations, representations that you need to understand as well. Leaching in terms of concentration and the way we do material balance is very different than the other separation processes that have been discussed previously. So let's look into these particular very important things to consider when you go already into your calculation part. Now, in a typical leaching operation, the solid mixture to be separated consists of particles. So, it has mentioned already in the first slide that your solute A or your constituent A is together with what we call the inert insoluble carrier B. So, we only assume that we are interested with solute A and the rest may be considered as the inert insoluble carrier B. It does not have to be that we only have two particular components in our solid mixtures. We can have several, but since we are only interested in A, the rest will be considered as inert solid or inert insoluble carrier solid B when we later on go into calculation. Now, we have to look into the solvent as the C. So, we label it the C or represent it as the C, and it is something that is added to the mixture to, take note, selectively dissolve A only. So, meaning it's not interested with the other solids in the mixture. Now, the overflow from stage, or if you have several stages in your leaching process, the overflow from the stage is free of solids. It is assumed that the overflow is all liquid and consists only of the solvent C that selectively dissolved A from the solid matrix. So again, the overflow does not contain any solid. What about the underflow? So the underflow consists of a slurry of liquid of similar composition in the liquid overflow and the solid carrier B. So what is in the slurry is the inert insoluble carrier B and a solution of the same concentration as that in the overflow. So whatever is the concentration of the overflow, that would be the same concentration of the liquid, which is in form of a slurry with your insoluble inert solid B. Now, in an ideal liquid equilibrium or in an ideal leaching equilibrium stage, all the solute is dissolved. So, we assume that all the solute is dissolved by the solvent and none of the carrier solvent or carrier solid is dissolved. In the sense that it is inert, so we assume that none of it will get dissolved by your solvent. all solute is being dissolved by your solvent C. The solute is A. Now, that is meant by all of these particular principles. Now, the mass ratio of the solid to liquid in the underflow is dependent on the type of equipment that is being used and the properties of the two phases. So, meaning how much of a solid you have in comparison to the solution that it is with in the underflow or in the slurry will depend on the type of equipment that is being used and the properties of the two phases. The two phases being referred here is the property of the feed and the property of the solvent. Now, leaching is essentially most of the time countercurrent. It was mentioned in the first slide. And in industrial leaching, the solvent and solid are mixed. They are allowed to come to equilibrium, meaning no mass transfer will occur already or will cease, and the two phases are separated. So, after they have reached equilibrium, the rate of transfer to the rate of reverse will be the same or shall totally stop. In that case, now we can separate the two phases. But the requirement is equilibrium has to still be reached. Now, the solvent phase, we call that the overflow. It is reached in the solvent, becomes more concentrated as it contacts in stage-wise fashion the increasingly solvent-rich solid. The underflow or the slurry becomes less concentrated in the soluble material as it moves towards the fresh solvent phase. So since the manner is countercurrent in terms of contacting of the two phases, the feed and the solvent, so your underflow is expected to be reaching an end where the solvent is entering your leaching equipment or your leaching system. So now it says here that your underflow moves towards the fresh solvent phase. So it's nearing that part of your equipment wherein it's going to be parallel now with the solvent that is entering the system or the equipment. Now, there are two categories of leaching. So, it could be something that is percolation. It could be something that is dispersed. Now, in percolation leaching equipment, so liquid is added to the solid. So, it is to percolate through the solid bed. So, the solvent is contacted with the solid in a continuous or batch method. And this is popular for extreme amounts of solids to be processed. So, as the term percolate, your liquid solvent is percolated through your solid, which is most of the time in the form of a bed, either stationary or moving. Now, in dispersed solids, it's the other way around. So, the solids are added to the liquid solvent. So, the solids are usually crushed into smaller pieces to improve or to increase contact area and to increase mass transfer before being contacted with the solvents. This is popular leaching method when an especially, so take note, high recovery rate can economically justify the typically higher operating cost. Why higher operating cost? Because there's a need for you to have a pre-physical treatment of the solid prior it to be added to your solvent. So you have to make sure that the surface area is increased, that way recovery is increased. And this is very popular in gold extraction. Now, again, this is taken from the CHE resources. Now, as to the equipments that are used during leaching, so it could be fixed bed. As I have mentioned, the solid bed is stationary. It could be moving bed, so it's the bed of solids that is moving, but still the solvent is percolated through it. And it could be dispersed bed leaching, in the case of the solid being dispersed in the liquid solvent. So, three equipments to facilitate leaching. So, let's go to the fixed bed. So, an example, you have here an example that is snipped from your textbook. This is typically used in sugar beet leaching or taking out sugar from beet. Now, this is used for extraction of tanning extract from tan bark and extraction of pharmaceuticals from barks and seeds. and the one that I have mentioned a while ago. So you have a simple equipment that adds hot water on top. It has a movable cover, and you have here the sugar beets in this case, and the hot water is going to leach the sugar from the solid, which is the sugar beets, and the sugar solution is going to leave here. So if you want to further extract the sugar from this solution, that would be a separate process already, but the leaching is just concerning here in this particular equipment. That's a fixed bed leaching equipment. Now we can have a moving bed in the case of the Bollman extractor and the Hildebrand extractor. So this time it is the bed that has the solid that moves. Okay. Now here in the Bollman extractor, an enclosed moving bed bucket elevator device is employed where there are perforations in the bottom of each bucket. The purpose of the perforations is as your solid passes through the pure solvent leaches out the solute from the solid. And furthermore, more trays, or shall I say more buckets, are being flown here. That way your pure solvent is going to leach the solute of interest from the solid inside the bucket. That is in the case of your Bollman extractor. Now the liquid that has the pure solvent and the solute from the solid is what we call as the mesilla. It's referred to as the mesilla. Now, as for the Hildebrand extractor, so it may consist of 3 screws, conveyor arranged in a U shape. So the solvent flows countercurrent through the the solid. So here you have buckets, in here you have screws in the case of the Hildebrand extractor, but both are utilizing moving bed in transporting the solid countercurrent to the pure solvent that will leach out the solute from it. Now, as to dispersed bed, we have this one. So it's often times used in systems of leaching equipment. So in here, you have several thickeners. We could refer them to these thickeners where your solids are being dispersed through the given solvent. So the solvent is introduced in each of the thickeners and your free solids are dispersed through them. So you have in each of our systems here a solid liquid slurry pump. The purpose is for the solid coming from this particular thickener to be reprocessed in the successive thickeners. The spent solids are taken here from the last thickener, meaning it contains very minimal amount of the solute already. Why? Because the concentrated solution, which carries out majority of the solute in the solid, is already being withdrawn in this portion here. So most of our thickeners actually class are operated on a case of dispersed bed leaching. So our equipments or our solids are being dispersed through the liquid. Now, what are the industrial application of leaching before we go even to the different computations that you need to know or formulas that you need to know regarding leaching to, let's say, have this appreciation of this unit operation? Actually, it's simple, but actually it's being used in majority of the industries that tries to recover a particular solute which is solid in form from a solid matrix. So it's used in the sugar processing industry. So primarily, as you can see here, in the extraction of some sugars, in the pharmaceutical industry, in the extraction of very essential oils, and in the metal processing industry, which is actually the most, shall I say, profit driven. Why? Because the product is very high in cost. Now, let's go to each one. So the sugar beets, the sample is the sugar beets. So from the CHE resources, your recovery of the sugar from this plant is one application of leaching. Another one is in the extraction of vegetable oil from nuts, beans, and seeds using organic solvents such as hexane. So again, this is a sample of leaching. And then we have the extraction of gold from ore. Now, a classic example here where majority of our alumni has been already employed is in the HPAL process of Coral Bay Nickel Corporation in Palawan. So it's using high pressure acid leaching in taking out nickel from ores. So they take out nickel, and that particular very expensive nickel is being shipped back to Japan for use, and especially in the electronics industry. So the process specifically used is high pressure acid leaching in the case of Coral Bay Nickel. The main product is nickel. Now, let's go now to principles involved in leaching. So in any mass transfer operation, equilibrium is a very important thing to consider because it dictates whether mass transfer ceases or not. So in the case of leaching, the solvent forms a liquid solution. Carrier may be totally immiscible on your particular solvent. So the carrier solid, what is meant here is the carrier solid of your solute. It should be totally immiscible with this given solvent. So some solution is normally retained by the solid and has the same composition as the liquid solution. And this refers to the slurry, wherein you have solids which has solution still remaining on them. Now, when the amount of the retained solution, take note, is constant, the system is said to be constant solution underflow. Meaning in the entirety of the leaching process, if this amount of solution that remains with your solid in the slurry is constant, then we have a case of constant solution underflow. Now, we have a variable underflow existing when the amount retained is a function of concentration. So, meaning, if the amount of the solution which goes with the solid in your slurry depends on the concentration of that same solution, then we have a case of variable underflow. So, take note of that. Here, the amount of solution retained by your solid is dependent on the concentration of the said solution. Now, here the stages, if we have a multi-stage system for leaching, the stages are numbered by the direction of the solid. If you recall in gas absorption in stripping, we number the stages based on where the solvent is introduced in the bed. Now, in the case of leaching, we number our stages based on where the solid or the feed is being introduced. So, we don't number it the way we do in the other unit operations discussed already. Now, there are very important assumptions here when we speak of leaching. Solute-free solid is insoluble in the solvent. This refers to the carrier insoluble or inert solid. The flow rate of the solid is constant through the cascade. The flow rate of the solid, this refers to the inert insoluble solid. Its flow or its mass flow rate throughout your system of leaching is constant. So from one thickener to another, if we're talking about a system, a leaching system, your amount of solid or inert solid is constant. It does not change. And this solid is said to be porous and inert. It is not dissolved in your given solvent. Now, the amount of solution retained by the solid in the slurry phase is dependent on. So, we have a while ago discussed that if we have a condition of variable underflow, the amount of solution that goes with the solid in the slurry is dependent on the concentration of that same solution. Now, in here, this is a different thing. We're talking about the amount of solution retained by the solid in the slurry, which is now depending on density and viscosity of the liquid, which is wherein the solid is suspended to, which is in turn dependent on the solute concentration. So this particular statement actually explains why the amount of solution that goes in your slurry together with your solid in the underflow is dependent on the concentration. It's because your concentration is dependent on density and viscosity. So, the solid in the slurry or the solution, the amount of solution in the solid in your slurry is dependent on the density and viscosity. Dependent on the density and viscosity of that same solution, which dictates that it is now the primary factor to consider when we speak of concentration of the solution. So the variable underflow concept that was discussed in the previous slide is connected here by means of density and viscosity. So we say the amount of solution that goes with the solid in the slurry is dependent on concentration, and concentration is dependent on density and viscosity of the same thing. That is why it now determines the amount of the solution that goes with the solid in the slurry. Now again, on the assumption, solvent amount is sufficient to dissolve all the solute in the entering solid. This was mentioned already. So we need not worry that we have a sufficient amount of solvent to ensure that all the solute is dissolved, and there is no adsorption of the solute on the solid. The solute remains only dissolved by the solvent, and as such it will never ever only get adsorbed or remain adsorbed on the inert insoluble solid. Now, solution in the liquid phase, the overflow, is the same solution that remains in the solid matrix in the settled slurry, which is the underflow, also mentioned already in the previous slide. Now, let's go to our representation. For a single stage leaching process, if this is our extractor, the extractor is the leaching equipment here, the slurry is labeled as LO, and this is the slurry which is fed to the extractor, and the final slurry is labeled to as L1. The N's here represent the inert solids in the slurry. Initial amount of inert solid and the final amount of inert solid in the slurry. Take note of the representation. Take note of the representation of the concentration of the slurries. If you're used with using liquid phase concentrations as X and feed concentration as X, in leaching we don't represent it as X, we represent it as Y. So YO for the feed and Y1 for the final slurry. B is the inert solid. So if you notice, this is just B and this is just B. Why? Because the inert amount of solid in the slurry at any particular time, whether it's in the feed or in the final slurry, is the same. Whereas this N is the concentration of the inert, the concentration of the inert in the slurry. So take note of that. B is inert solid while N is concentration of the inert solid. Now our solvent is still labeled with the V's. So V1 for the shall we say the solvent that carries already the solute, and V2 for the pure solvent that does not yet carry the solute. Now look at the concentration in which we represent for the solvent. We're not using Y, but rather we're using X. It's because in leaching we exchange the manner of representing the concentrations, just like the way we do with the other previously discussed unit operations processes. So we exchange. The feed will have Y, or the liquid phase will have Y, and the solvent phase will have the X. Now we will look into specifically what is this N, what is this Y, and what is this X, and even what is this B, because it's in detail discussed in the next slide. So N is the concentration, as I have mentioned a while ago, of the inert insoluble solid B in the slurry phase. If you're wondering why take note of the N, wherein in the first place we know that this B is not changing. We have already placed it, known it that the inert solid will not change from one thickener to another or from one equipment to another. Then why is this going to change? That is the concentration of the inert soluble solid B. It's because the denominator changes. The kilogram of A plus kilogram of C in the denominator as we go from one equipment to another in our leaching system changes in value. So that is why the concentration of the inert insoluble solid B changes, because the A and the C changes. A is the solute, C is the solvent. Now I said we will look into the XA and the YA. Now, XA is kilograms A per kilogram A plus kilogram C. YA is kilogram A over kilogram A plus kilogram C. If you look closely, nothing changes. It's the same. Both formula is the same. However, for XA, that's a representation for the overflow. And for YA, that's the representation for the underflow or the liquid slurry. And one thing very important that you should take note here, class, the denominator does not take into account the inert solid B. So your concentrations in leaching processes only takes into account in the denominator the A and the C, the dissolved A and the solvent C. It does not take into account solid B. That's the same thing when we have later on our L's and our V's. I'd like to go to that part. The L and the V here only takes into account the A and the C. If you will consider, specifically, we won't have any problem with the B because anyway, here the B is just all C. Where in here, the V is A and C. But in here, we will have a very big problem if we forget that these L's only take into account A and C. It does not take into account the inert carrier solid B. So take note of that because that's always the major error, cause of error in leaching problem computation. So the representation, this is for the solvent and this is for the feed or the slurry. And this one is the concentration for your solid B. Now, our feed is, of course, having the concentration kilograms B over kilograms A only. Why? In terms of N, because our feed does not contain our solvent yet. Unless if the problem specifies that your feed contains a little of your solvent C. But most of the time, class, your feed does not contain the C. Now, your YA then is said to be 1.0. Why is it that you have only YA is equal to 1.0? It's because, again, we don't have the C in the feed. We only have the A. So it would be kilograms A over kilograms A, and that would be equal to 1.0. As for the entering solvent, we don't have the solid. Our solvent is pure liquid, so it does not have the inert insoluble solid B. In the same way, if it does not contain the A or the solute that is to be leached out by it, then of course its XA will be 0. It will only have XA after it has already dissolved solute A from the solid matrix that it is contained. Now, in terms of mass balance, so we add up all the, shall I say, the phases that contacts or enters the leaching apparatus, and we also add the phases that leaves the leaching apparatus. Again, I put this in red. We only place in here the solute A and solvent C present in this particular phases or feed and solvent phases. Now, when we do component balance, so we copy it from here, just like what we do with the other unit operation processes, and we affix the correct concentration representation. So, if it's liquid and if it's feed, that's Y, and if it's solvent, that's X. Again, X and Y here only accounts for A and C. What is unique also about leaching, it has so many things unique if compared to the other separation processes, is we can do solid balance. So the solid that entered should be the same solid that left your system. And it should be the same solid that should be represented in the bulk phase, or that should be present in the bulk phase. By the way, this M also represents the bulk phase, where your solvent and your solid is contacting each other. XA is the representation of the concentration of A in your bulk phase M. So we can use any or all of these material balance equations, total, component, and solid balance when we encounter leaching problems. If we have a case of multi-stage leaching, the same principle applies in single-stage leaching. Only that this time we have to consider several stages. And in here, everything is defined. So, XA, composition of A in the overflow, YA, composition of A in the slurry. We have V for the overflow solution or the solvent, and L for the mass of the liquid slurry or the feed. And we have B, the mass of the dry solute-free solid. And that is referring to the inert solid B. Now, your principle here when you make overall material balance for multi-stage leaching processes is the same. You just make A and C balance. And you just add up also the streams that enters and the streams that leaves. When we have component balance, the same thing. If you want to add another equation here with solid or overall solid balance, nothing, no harm will be done. It's because in principle, we can do that also. It's just that we will have solid in the feed equated to the solid present in the final slurry. Now that ends the topic on leaching. So please go back to your textbooks or solve sample problems on leaching based on the simple 3 material balance equations concerning this particular unit operation process.